Morning. Morning there. Hello.
Good morning.
Good morning, guys.
How are you guys?
Tired.
Yeah,
Morning,
I know.
guys.
Morning. Go ahead and get everything together here.
Morning, Srini. I'm not sure if my
Good morning.
friend Ramya is going to join.
Let's see here. I think I added him to the group. Join the meeting, says Srini. I'll just put the link to the Zoom here too. All right. Let's give a few more minutes here. How did everybody do this weekend?
I can't hear you, Vijay, if you're talking.
Oh,
I can hear him.
you can?
Yeah, I can hear.
Okay, great. I was just saying, how did everybody?
Is it me or?
Can you hear me, Amulya?
Oh, hold. So it looks like it's me. Okay.
Okay.
What's going on?
So we've been going through chapter 1. I think we're almost done here. I think there was only a few more pages on this. So we can probably finish that, or we can just kind of move on to chapter 2, which I know people wanted to do as well. And we can talk about some of that as well. So I guess like maybe let me just see how we're doing as far as like participants. I think we have 3 people so far besides myself.
Yeah, I read up to chapter 3.
Oh, wow. Good job.
Yeah,
Do you want?
sorry.
Oh, okay. I was gonna say this time around, I was wondering if anybody wants to kind of go through the chapter and proctor. Like I was thinking maybe we can take turns. That might be
Yeah.
kind of fun.
Sounds
So who wants to do that? Do you want to do that, Amelia?
I'll
I
do
can
it.
Oh, yeah. Okay. Yeah, sure. Go ahead, Joy. Yeah.
Okay, so like, okay, my questions were more persisting towards like the end of like chapter 2. So like, so far in this like book, they're kind of giving like an introduction into like these different core concepts of like reliability and sustainability, and what these terms mean in terms of like what scalability is and what it means to like write an app that can like scale and works like that. And then we get a few examples that they give us here of like how Twitter implemented like their back end to send like the tweets out and how they were running into like issues. So I guess this is to give you like warm-ups into thinking about how our data is like being like distributed and like how we're going about doing this. It's kind of like an abstracted layer coming from like a developer standpoint, I suspect, because like when we program this stuff, I know me personally, a lot of times I don't particularly think about this kind of like context like this about as far as like how like tweets are being sent out and broken up and divided and everything like that. So like for me, when I kind of looked at this chart that we're looking at right here on this chart, where it's like I see it where it says like user post tweet, and then it shows like all tweets T8 through T1. I look at that as like being like an array or some kind of like a dictionary that's storing like all the tweets. So like you have T1 through T8. So those are all variations of the tweets. Could be up to NT, truthfully speaking. And then it shows that you got the different recipients. So I guess this is all like theoretically like how you're supposed to like break it down before you code it, I suppose. It's like the pipeline, right? Is that like, because I'm trying to understand like the whole purpose of this book, you know? So is that the kind of like abstraction that this kind of like talks about, like predominantly? It's like how to go about like organizing your data more or less?
Yeah, I mean, Amelia, do you want to explain this diagram? I think like, like you had a good idea last time. You kind
Yeah.
of, yeah.
Yeah, so basically the Twitter, so basically the diagram is showing one of the approaches
Like
to
a relational, right?
this is first chapter, right?
Yeah.
The first
So
chapter.
This
in the
first
first
chapter.
chapter we are yeah. So okay, yeah, this is the first one. Yeah, so simple relational schema. Yeah. So basically what they're saying is, yeah, there are the traditional way of actually looking up each tweet from all the people that a person is following and kind of merging them together when a user's homepage is being loaded, right?
Mhm.
That's the straightforward way to do it. But then the problem there is it does not really I mean, there is a better, like as the user base increases, there's a you see that some of the people's tweets are getting loaded more, and it does not scale as well, right? So there is a better way of doing it, which is to separate out the separate the users who are being followed who have a huge fan base, right? So you kind of proactively push their tweets into users homepage data structure, so that you don't have to do that work on demand.
On demand.
Okay, so then that's really what this is. This is kind of like a warm up to like giving you the examples of the various like data structure implementation. Because if you go into chapter 2, then it gets into like non-relational, where you have like many to many relationships, and then it goes into like node based, which would be, I guess, like a graph based or graph related data structure, where you have edges that are connected to like vertices, and then the vertices connect to the head to the tail from each node, from node 1 to node 2. So I guess that's what this is then. It's kind of like giving us a few examples of different implementation with some I guess context to go by, right?
Yeah, so the main thing here, Joey, right? Like, and I think anybody kind of knew, like watching or coming into this, is that it's all about just how to engineer stuff better, right? Like very, very simply put, forget about data structures, forget about algorithms, forget about like, like all the buzzwords and tech terms in here, really, right? It's just like how to like make, the thing that you have, your application, like more performant, better performant. And there are a lot of like tricks and tools you can use. There are a lot of ways to redo the algorithm. And like in this case, right, we have, this Twitter example where people are getting tweets, and like we were saying, right, like you can get all the tweets on the page load, right? You can select everything from the database. And that's going to take some time, especially if there are people that have millions and millions and millions of tweets. Then it's just going to take a long time to get that on the timeline. So
like, I get that. Like, I think my question's more like, so based off of knowing what they've just showed us and what we've read, even if we just go off of this, like example right here, like in a real life scenario, like how would you identify like which of these schema techniques would be best for your edge case that you're trying to implement, like you're trying to like work through? It's like, how do you go about mitigating like what would be the best schema to utilize for best performance?
So it doesn't happen immediately. Like people have to work in teams and assess like what's going on.
Right.
Like they're saying Twitter here, right? They're not saying some guy at Twitter like came up with this approach, although that could be the case. I mean, like you're saying the team did it, right? So
Yeah.
it's part of the analysis, right? The team looks at, what are the choke points on their application, and they think, okay, like this is where we see, most of the,
Right.
performance lacking, or the bill is really high for us, right? Like the SQL call is going to take us, before, when we were a smaller application, we didn't really care, but now
Yeah.
increase load, right? Like increase scale. Now, like we're doing the SQL call all the time. Maybe we can just push this, into a cache before the user opens
Right.
the application.
And
But
is this still being benchmarked on like time complexity, as far as the number of actions we're counting that each operation takes, and the how many like functions are being executed and stuff like that? Is that how this is measured?
yep, all the time. Like they're always like looking at that and always thinking about like, how to
Okay.
make it better.
So basically, where the latency usually comes from, right? It usually comes from discretes. So you need to have some kind of instrumentation metrics around around stuff that will take longer time. So in our code base, at least in where I work, we always have those, the time, basically the latency metrics around DB loads. So we know where and when basically when a request is processed, we have a breakup of where the time was spent. I mean, it does not happen like in the first iteration. You kind of see that, okay, we don't have the visibility, and you keep adding the metrics. And so usually after some time, you have a good visibility of where the time is being spent, and your whatever latency that you are trying to achieve, and you kind of optimize on that operation.
Yeah, and it's not like everything, like their solution to, using a cache, like to reduce the amount of SQL calls is like a great answer, because they tell you too here that, if they do this pre-work to, get the posts in advance, that's still going to be, very heavy and require a lot of work. So, they opted for a hybrid approach here, where depending on
Might
the
not even scale, right? So
Mhm.
if a person is being followed by a lot of people, and you have to load that particular record so many times, right? The same record so many times. So basically, it's disproportionate use of disk. So
So
basically,
everything's preloaded into the cache.
assuming, yeah, you have cache optimization, then yeah, basically this is an alternate. By the way, caching is another way they could have solved this problem, by having an in-memory cache and kind of having a subset of users who are power users, right? So having those tweets in cache, that could have been one of the
Okay.
one of the
So
ways.
so by loading the tweets into the cache, then it automatically is going to be loading to the user before the process finishes, right? It's kind of like
They could
preloaded.
not, yeah, they don't have to go to the DB, but then I think the way the user model they implied in this is that basically every user has a homepage data structure that gets updated. So that approach of fetching from the cache, I don't think they follow that. Basically, they have a homepage that basically that's constructed ahead of time. Like for example, if you go to the homepage, right, you can. I'm not a Twitter user, but I don't know how long back can you go back? Like, can you see like 1 year's worth of tweets in that?
No, this is within the last 5 hours or 10 hours, but I get
Okay.
what you're saying, because it's loading them into the cache, everybody's tweets, right? It's kind of how it preloads.
Right, but if the homepage is expecting that I get 1 year's worth of tweets from that all the user has been following, then it's essentially an incremental thing, right? So then it probably, you anyway have to go to the DB if you want to fetch 1 year's worth of data. Like you
Right.
can't cache all of it. In that case, maybe, yeah, it makes sense to have, like, have a separate record, and you kind of add them
Accordingly.
preloaded instead of kind of do it from the cache, because cache does not scale.
Got it. Because the cache is like a lazy load, right? It's only going to take like a portion of the data that's being stored, right? Because
Yeah.
the cache is like it's almost like a temporary instance of the data, right? It's like it's a snippet, right? It grabs like the cache, whatever the parameter is, from 0 to whatever that I guess you could say a rule that you set, that parameter, right? Like if you said 8 hours, that's a parameter, right? Or if you said, like you said, give me the tweets for like the last week or the last month, right? That's a parameter, right?
Yeah. So
Okay.
it's very application specific. So you need to understand, use case specific. So I think, yeah. This is optimized for Twitter, but yeah.
Yeah. So, this is a good example. Again, like I think, we can talk about it more offline, like on the Discord. This is, something we'll probably come back to as well. Like how would you design Twitter in our own like study example? This would be like something we could work towards, later as we get through the book. So yeah, I think we have a few more things in this chapter. I just want to ask here, does anybody have experience doing batch processing, or does anybody want to explain what that is?
I mean, we do batch processing in our application.
Mm-hmm.
So usually batch processing, we in our application context, what it means is we have an asynchronous worker that is basically reading off of a SQS, like a queue, like Kafka queue kind of a thing. So and those messages are getting processed, and usually it's a long running thing. It's not, we kind of intentionally designed it not to be latency sensitive. What that means is sometimes it takes longer. These messaging systems have a timeout, right? So in order to avoid this timeout, hitting the timeout, we kind of split our work into batches and kind of do it in the like a slow burner kind of a thing. But
so are these batches running on their own thread then in the background? Are they running like independently?
They are running independently in the sense that, yeah, so basically it's a recursive thing. So we start the process, and then it processes a set number of records and then sends the next request
So
for
it's
the next
constantly
batch of
calling itself then.
Yeah, it's not, it's publishing. It's not exactly recursion, but it's basically queuing a new message for the next batch to be processed.
Okay.
For the workers to pick up. So, but I don't know how, I don't use Hadoop, so I'm interested in listening from people how
Yeah.
it is done.
Yeah, definitely. I haven't really used Hadoop either, but like I've got friends in the video game industry, and they really rely on Hadoop or similar processes to, go through tons and tons of records, just like you're saying, because there's a lot of video game data, right? Like your level up, right? Your, like what level you have, like what, gear you bought, what kind of like material you have in your character. And so all these things have to be mapped and then reduced in real time. And so they have to do like tons and tons of batch processing. If I get time, I'll try to find somebody from that industry, like to either give a meetup or talk about it at some point, because I think it is pretty interesting to go through it. Okay. They did talk about latency and response time. And so I think that's an important topic. I think just for now, I'm going to just make a point that it might be worth it to just kind of, highlight this area so that you're understanding that. Then
basically they're saying you have to define what is load for your system. So if it is an API, if it's a REST service, it's an application service, then latency and availability are your parameters, right? If it's a batch processing system, then it's the throughput. For batch processing system, it's not clear what, for application it's pretty clear, right? Latency, time taken for a request to be processed. What is, you have to be a little more technical when you're defining the throughput for a batch worker, and defining the limits of a batch worker. When is the time to intervene and maybe reduce the batch size, or so that it takes a little more effort to define load parameter for a batch worker than for a straightforward REST service.
Yeah, exactly. Like throughput is really important. It's the number of records per processed per second on the batch, or the time it takes to run a job, right? So that's important when it comes to a batch. What's the throughput?
Is throughput different than output, or is that just another word for output?
They're kind of similar. I think throughput is just more like, the technical term for, just how many records you can get done per second, or the total time output, and it relates to time.
Okay.
Output is more just kind of like a unit, like, oh, I get like, 10 widgets, out of this. That's the output. Or, like input, like some, like a coin, right? And then the output is like, I can play the game, right? You're not really thinking about time.
Okay, so throughput's more just concerned with the actual time. Like,
exactly.
for the completion to take care of itself, right?
Exactly, yeah. So, and then there are other terms again, right? Like, so I'm saying like response time is like what the client sees. So, like when you're opening a web page, you'll be like, oh man, this website's taking, like 10 seconds for it to load, and I want it to be fast.
Right.
That's response.
So would latency be like the cache? Latency is like the cache of like the request, and then the response time is the actual response measured through throughput?
No, so like latency is basically like just it says here too, a request, right? When you make a request, how long does it take to be handled? Forget about things again like cache. Remember, cache is like, the application of some of the terms. This is theory, so latency is like, like when you're wearing like your headphones for Bluetooth, that's kind of how I remember latency. Like, oh, if they say low latency, like when they advertise a product, that means like, like the signal from the Bluetooth comes to your headphones and gets processed pretty quickly. So like,
that makes a lot of sense.
If the latency is pretty high, then you're going to see like, like gaps between like what you're watching. Like maybe the speaker sound is going to be later than like when their lips actually move. So you want low latency. Same thing with a video game. When you're playing a video game, you want low latency, like the whole thing. That was the thing with Google's Stadia, right? Like you're playing like one of those video games on their servers, but if it's high latency, and their output is pretty like low or whatever, right? It's gonna be
right.
Crappy game. So
I guess no one wants to look at loading screens.
Exactly. This is like super important. All this whole stuff here is like super important if you're like in video game development. So yeah, it's a hard problem to solve.
That's true, because you see more of that latency than any other applications that you use because of the loading of all the assets.
And those are usually the trickiest ones to solve. How do you improve latency? So
yeah,
you will have to redesign. So yeah,
and they were also kind of talking about like sometimes you have to look at charts, right? You can't really just kind of know like off the top of your head or like looking at a system. You have to really kind of look at the charts and understand like, what are the outliers that take a lot longer. So they have like these graphs, right? And then they have like these different levels. So what is the median? What is the mean? What is the 95th percentile, 99th percentile? And so in their example, they talk about like servers and racks, or mechanical vibrations. Those are things that you can kind of look at. Median is like, like there's mean, which we probably all know, right? Like mean is like on average, what do people experience? But the thing is like average really doesn't refer to any particular formula. It's not a good metric if you want to know your typical response time, because it doesn't tell you how many users actually experienced a delay. right? An average is just an average, right? Like it's
It's a group, right? It's
a
like a
group.
batch.
Yeah, it's not an individual person. So that's why they split it up into these percentiles. So if you have median, right, then that means like half your requests, right? Like if you're looking at like response time, like for a website, which is this, maybe this example here, then median would be like 50% of your users experience, you know, a response, which isn't less than 200 milliseconds. And you might think, hey, that's pretty great. But, you know, you also have to look at the outliers, right? Like what's the 95th percentile, right? What's the 99th percentile? And you might think, oh, well, why would we care, right? Like 50% of our users are doing great. But if you have, again, like, remember this book is about like scale. And so if you have, you know, like millions and millions and millions of users, and 95% of them are, you know, experiencing kind of like longer, you know, delays, it could hurt your business, especially if like, let's say, you know, 1 million people experience an outage that day. What are they all going to do? Where are they going to go?
They're gonna go somewhere else.
They're going to go on Twitter and complain.
Yeah.
Right. And so if they go on Twitter and complain, right, then, you know, like other people are going to think, oh, hey, maybe this thing doesn't work today. And so they may not even come to the website. They'll just go to a different shop, right?
Yeah, or they'll leave.
Or they'll leave. Yeah. Like,
No, but like forget latency, right? Like it's an indicative of something bad that's going to happen. So if your P95 latency is showing a sharp spike, it usually indicates there's a regression. Like if you're doing a rolling deployment, right? Like you are basically updating the servers, some servers at a time, and your P95 spikes, what it means that there's some bad code rolling out, which is pushing your latency higher, you know. So it's an interesting, it's a very valuable data point to monitor the health. So if a particular host is if there's a bad host, right, if it's basically something is wrong with the host, then all the requests going to that particular host are kind of taking longer. So it's
so I run like Lightbox or some kind of like a tool to like measure it, like after you deploy it, kind of a thing.
Yeah, so basically you it's so if for a large service like AWS, right, so our fleet size is usually like hundreds and to like upward 100. So it's not possible to monitor each and every host. So we kind of look for pointers to what could be, you know, this is a metric that we use. So we look at P95 when the things are getting deployed and know whether it's all good or it needs some investigation.
Yeah. So, just make a point here in the book, like if you are, interested in this, and I think we can also come back to this and look at this example a little bit more. One thing to kind of note is that you might see sometimes, like if you're working with Amazon, some, terms like SLOs or SLAs, right? And so this is something that they advertise like quite a lot, in their business. If a service is up, it has a median response time of less than 200 milliseconds and a 99th percentile of under 1 second. So, if these metrics are set, then, the customers pretty much understand, oh, wow, I'm going to have uptime of mostly less than 200 milliseconds. And the service is going to be up 99.9%. How many people here actually know like what the actual number is for Amazon, like their SLA?
Time?
I know.
Are you speaking in terms of like uptime, like their uptime allegations?
Or I'm talking more in terms of just service level agreement. So that's just the function of it.
Oh, shoot, I'm not sure. They have so many different service. It's going to be a lot of SLAs.
Yeah. So
every product, they have different SLAs. Most likely,
I guess it would be contingent on whatever service you're using.
So if you go to here, right, it'll tell you like
Route 86 is their deployment.
100%. I see CDNs in every cloud provider. they provide 100% uptime. I don't know how they do it, but yeah, that's amazing.
Right, here's Chime, which I think
CDNs and
I've heard
DNS.
about, yeah, many times. So let's see here, EC2. So EC2, monthly uptime less than 99.9, but equal to greater than 99.0, 10%. Service credit less than 95% and 100%. So that's good. So that means you can rely on EC2, like if you use it as a service, or EBS or ECS or AWS Fargate, any of these like web services, it should be up most of the time for 95%.
That's good.
So
What
I
is
guess the
full
only
SLA?
time that
What
would
is-
ever change is if
what
they
is
had
full-
like a fire at the facility or something.
wait, what did you say, Amelia?
What is full SLA? Because this is less than 99.99%. It's not very clear what exactly has been there. But equal to or greater than 99% service. What is service credit percentage? I never looked at this. Interesting.
So they refund your money for this for the compute cost if they don't meet it, their SLA.
Yeah, you'll get back 10% in terms of
Mm.
credit.
Oh,
I
but this is
think-
not. Go ahead.
Yeah, so I think only Amazon does 100% refund for less than 95.
Right here.
Yeah, that's documented. Actually, that's great. Azure. I mean, I work primarily in Azure, and there was 100% credit if they don't meet their SLA.
So let's take a look
I
as
think that only changes like if they have like something happen at the actual physical like distribution center, right?
Yes.
That's
yes.
the only time that number would change, because then it would mitigate to the next distribution center in the region, right? Isn't that why they have different regions with service centers?
it
Yes,
says,
this is in. Yeah, sorry, but
oh, actually, go ahead. Go ahead. I'll jump in after.
yeah, this is at every individual resource level. If your application composes of many components, right? You need to so again, that was also mentioned in the book as well, right? SLA is not from a customer or from a customer standpoint, customer to the AWS, right? Your SLA is your SLA of your application. But when you're using AWS, you might use 100 different servers. So you have to look at each and every SLA of each resource.
But
Correct.
you should be able to come up with a historical SLA number, right? For like over a month or so. Slack does that. Like it's pretty bad. It goes down pretty often. But yeah, I was interested in that number for AWS. But anyway, if I find it, I'll let you know. Let's get on with the first chapter.
Of course, yeah. Okay. So yeah, so basically the whole point here is just like uptime and latencies, which we discussed. There's also a term called tail latency. So, just make sure that you read that point. I am kind of going faster because we do want to finish this chapter and go to the next one. Let's see here. What was this page about? Let's see here. When generating load artificially in order to test the scalability of the system, the load generating client needs to keep sending requests independently of response time. If a client waits for a previous request to complete before sending the next one, that behavior has the effect of artificially keeping the queue shorter in the test. And so, like there are just, techniques, I think, let's see here. Because when you're dealing with percentiles, right, high percentiles become especially important in backend services that are called multiple times as part of serving a single user request, right? Like, so if you're making a request to a web page, sometimes there might be multiple services that have to be called together and they all need to be up. You have to have like that guarantee that this is going to be up most of the time. So if you're not, if one of those things goes down, or if one of those things is slow, then that may actually make the whole thing slower. And so that's something, an area that you probably want to investigate. This is the tail latency amplification. So another point to just kind of highlight and keep on, top of when you're reading through here. And then like they say, you just want to just, look at charts. You want to look at like how the requests are coming in. There are good ways to do that. You can use algorithms as well to kind of help you, like for DK, tdigest, HDR histogram. Let's go on. And you can kind of aggregate the response data, so you can see like, where you're getting the least, or like the slowest, uptime. So here, there's like a graph here, or this is like a chart, shows you the web application that is making, requests to a backend, and it can show you like this backend here is 92 milliseconds, this one's 76, this one takes 103. This one's the longest one, 487, right? This one is probably the service that is the slowest. So you just kind of have to, look at the charts again when you're going through these. And then they talked about.
Is this how you monitor? Like you guys, is this how you do it in your services?
Yeah.
Like,
yeah. Mm-hmm.
What we do is, I mean, this is sophisticated than what we do. So we just have dependency graphs. So in our basically in our dashboard, we have a dependency section for each of the backend calls that our services making calls to, and we basically monitor latencies. Basically, we monitor P100, P90 latencies on all those dependencies, and we look at our own basically the aggregate API latency. So if there is something that needs to be investigated, if we see that P95 or P100 is spiking, then we look at the dependency graphs. Okay, who is that fault here?
Mm-hmm.
And kind of go like that. But this is interesting. This is like you do that breakup for the first P100 request. Is that what it is? Like for the max, for the slowest request, you have that breakup on your dashboards?
Yeah, and I think this is just, again, like the books example. So it's textbook, but you're right. I mean, like there are different ways to do it, like your company's implementation can be, looking at like the dependency graph, which is also like, it's just as fine, right? Like as long as you just kind of are able to aggregate that data and say, oh, okay, this is like the aggregate response time. Like how you look at the data yourself really is just kind of like what you decide to do, later for like, optimizing your servers. So, I think, don't get too tied to the way the book does it. Like
no, I'm interested in alternate ways to monitor. Is there any better, smarter ways to do this? Ours is kind of naive. So okay.
We can come back to it, like I think would be a great point to kind of look into, or if anybody here, like, or anyone later kind of is watching, you can like share it here as well as the WhatsApp community.
Yeah.
And like Medium articles, or any kind of articles that you see on the internet. Okay, so then I'm gonna just kind of keep going. So one point I liked in this book was scaling up, and the concept of vertical scaling and horizontal scaling. So like when I think about vertical scaling, I think about like increasing like the machine that I have already, like putting more RAM into it, putting more hard drive space, just making it more performant. Whereas horizontal scaling is like, okay, I have multiple machines, right? Like, I distribute the load across smaller machines. And both of these techniques pretty much work, right? Like even like at home, I always use this example here where like I stopped buying like the most powerful like computer out there, because I always felt like, in the past, my old self would be like, oh yeah, I need, like the highest processor, the best RAM, the best storage space, all that stuff. That's an example again of vertical scaling. But then I realized, well, I can get a lot done with the basic machine, even if it's like not as good as like, the best one out there, it still works. And then I may only need it for like a couple tasks. So if I buy a basic machine, I'll still have money again for some other basic machine. Then I have two basic machines that can handle multiple, tasks from my home. So I feel like this horizontal scaling is also a great approach if, you know, you're thinking about like, how do you want to distribute load? You don't always need the most powerful computer, but then there are cases where you do need powerful computers, especially if you're doing like movie editing, or like, you know, you have some application that is doing like high intensive tasks. So you have to kind of like do a good pragmatic mixture of both approaches. So that's what that part was about. You know, and then elasticity, and you'll probably hear this term a lot when you're looking at, you know, Amazon sites or, you know, Azure sites. And that just basically means like automatically adding resources, especially when load increases. So that's kind of a nice feature. You know, you don't have to like go and like buy stuff, you know, buy computers to like handle your load, you know, so these sites like Amazon will do it for you like on the fly. So it's pretty great. Any questions on this part here so far about horizontal versus scaling?
I'm good.
Okay, cool. So let's see here. So then the next part, let's see here. So this part, it just basically talks about, you know, there's no one size fits all to the architecture. Like there's no like secret sauce or like how to like do this. It's just, you have to kind of, you know, look at each thing case by case, you know, and look at the problems, like maybe volumes of reads, volumes of writes, kind of like in the Twitter example, volumes of data to store, the complexity of the data, are you using the right data structures, the response time, looking at the histograms, looking at access patterns, and then kind of like decide how you're going to design a system that can handle, you know, a lot of these different requests. So
it's kind of like writing a protocol, huh? You're kind of like thinking ahead of time and trying to like mitigate between like what you have and like look over everything and try to say like, okay, well, here's one approach, but then this is like potentially a downside that I could face with this. So you have to kind of like look over each I guess like design schema, right? And like kind of analyze it like that, like pros and cons.
Yeah, exactly. You know, like just kind of looking at your system and really kind of fine tuning it, understanding like where, again, like if we go back to the whole chapter, right? Like this whole thing, like as a summary, it's telling you, you know, like it talks about reliability, scalability, you know, load. It talks about like handling like requests, strategies for handling requests. Like maybe you could get all the requests at runtime, or maybe you could cache some of those requests in advance.
Makes sense.
If you hybrid all that, you might get the most optimal performance. But then what is performance? Being able to look at like the CPU, the memory, the network, the bandwidth, you know, the throughput, latency.
So it really just revolves around how you're processing what data, right? Because like
exactly,
you could have like an image, that's one type of data, but it's like stagnant, right? It doesn't do anything, it's static, versus a text message. It's more of a dynamic operation, right? Because you have like messages that are being sent, messages that are being read, messages that are being cached, messages that are being like preloaded. So it's like a little bit different like way of how you're looking at things, right? Or how the batches are operating.
yeah, exactly. So, and like I said, we can go through a lot of this later. Like I think right now, like for this, you know, session and for the sessions coming up, it's just getting like familiar with the terms, the theory, because like once you kind of understand like the terms and the theory, a lot of this is like easier to talk about like later when you're actually kind of, you know, going through exercises. It'll make more sense as it comes alive in your head. So, but yeah, the whole point here is to just think about scaling, think about like handling like loads, and like being able to understand different kinds of charts and graphs and data, because like that way you can like make good decisions about what's what kind of, you know, like choke points you're having in your application, if really anything, and how you can design some of that stuff better. Maybe like approaches could be like, you know, vertical scaling or horizontal scaling.
Gotcha. Because you want to be able to handle like the additional like user load, right?
Yeah, exactly.
Like Netflix,
Point.
like for example, like when The Mandalorian came out, or Disney Plus, right? I heard when that show came out, like they were not accommodating for all the extra users that they were going to have on the premiere, and I guess it crashed like their whole system, and their system went down for a while.
Yeah, exactly. So this is like for pretty much like any kind of like new thing, right? Like anytime like a new service comes out, you can kind of expect that there's going to be, some early on issues that they have to kind of
Right.
figure out. And so part of it is the scaling. So it's really important. That's why
Okay.
like, this is tested in like, programming interviews.
The thing that the caveat here is that you can scale what is in your control, but if you have dependencies, right, they don't scale along with you, right? So
Right.
you have to architect your system that kind of accommodates the slowest player dependency on you, or like work on phasing out that dependency. So usually in most of the applications, the slowest thing is the DB, right? So like you can have you increasing the fleet is not it's so simple with Elastic's EC2 auto scaling and stuff, but what do you do about hard dependencies?
Okay.
So that's where the hard problem is. So you have to kind of you have to solve the problem on a use case basis. Like if you know that DDB is like your database is the choke point, then you have to work on introducing caches, and with caches you have other issues like the cold start.
Okay. So you
So
basically take the problem and you like basically create like a wrapper around it, and like try to like, I guess, mitigate that, like reduce it by, a further implementation of like another service, right? So like if we go back to the example of, like I said, like how like Disney Plus like crashed and stuff like that, then they could say like, well, in that example, they could have been prepared ahead of time and thought about it, and they could have had like, a load balancer in place to, two extra load balancers maybe to accommodate for, between the hours of like 11 a.m. and 9 p.m. we expect like a heavy spike in users. So just in case, then we have these to, be backup in case everything crashes, then it'll spin everything back up. So is that kind of like the thought process with this? It's like when we're like,
no, so I was talking, yeah, but what you spoke is a good point. There are so if something like that happened, it's essentially an engineering fault, because there are many services available that handle that particular use case to kind of monitor your application pattern, usage pattern, and kind of provision resources according to that. AWS has this auto scaling service, which basically brings up new instances when you can define the parameter. Like if you see the TPS, the total number of requests that are getting processed is high, is more than like some 1,000 per second or something, then you say, okay, I want more instances, I'm anticipating more load, so bring up more instances, and you can define those rules. But what I'm saying is that this scaling out is a very it's not as straightforward as it might seem. Like just bringing up servers is the easiest thing you can do, and it does not solve all the problem. The real problem is the dependencies. And you don't control them, so you cannot scale them. So you have to basically work around them.
It's a lot of stuff you have to think about when working with data, huh?
Right. So has anybody used Hazelcast or stuff like that, like the DDB caches?
Well, what was that again? I'm sorry, I didn't hear.
Hazelcast, I think it's called. I have not used it, but it's one of those Hazelcast.
I haven't used it, but
I haven't used it.
Glad you bring it up.
Yeah, I mean, we had an outage because of this.
Okay. This is your slowest.
No, it was supposed to solve a problem for us, and basically you have to understand if you are basically taking in a dependency, you should understand the limitations of that dependency before you kind of full on implement it, like integrate with it. So we had like, it was very hard to recover from because we didn't have visibility into what it was doing. And we took a pretty, and we kind of phased it out. So
Okay.
Well, that's a good thing to know about.
So this is something you should definitely talk about like in like the threads later. Maybe we can bring it up.
Yeah, it's kind of handled by a different team, but it's all this application, same application, microservices. So it was handled by different microservice team. But yeah, I did not directly work on it, but I know that that was the root cause.
Right.
Anyway, let's go. Yeah, so
working with cloud kind of the benefit of like they handle a lot of this stuff for you.
Yeah, but you still want to like engineer, right? Like this yourself, because ultimately, if you're just kind of relying on another provider, you're not going to know, like, you just like put everything up there.
So you still want to wireframe this out and basically map it out like a flow chart, right? Of like, is that what you call it? Like a flow chart?
Yeah, basically just kind of like some kind of diagram that kind of shows, here's my application, here's all the components in the application. You have the client, then you have the caching level, you have like the calls to the database, and then maybe like how the database is able to handle scale. Is it horizontally? Is your application like vertical, or is it horizontal, or is it a mix of both? And then how many different so we'll come back to that though. Like I promise we'll come back to it. I just want to keep moving forward. So the last part of this chapter is called maintainability. And I think like this is the part that everybody kind of like gets intuitively. It's just, like the idea of like being able to like keep the system that has been designed going, like preventing, like, I guess like the ongoing maintenance, how will we fix bugs, keep the systems operational? How will we check the failures? How will we adapt to new platforms, kind of like Hazelcast, right? Modifying for new cases, tech debt. This is like a term that I didn't really know, like when I first started, working. Tech debt just basically means that, just like you have regular debt, like financial debt, right? Tech debt basically means that like you have some stuff that you're gonna do, but you're putting off for now, right? And you'll come back to later, right? Like in the case of money, like you're like, oh yeah, I'll pay this later. But tech debt, it's basically like, that there's an issue with your program, but you don't have the time to solve it. So you're going to come back to it later and just for now write a patch, but later you'll come back and you'll do like the actual, refactoring, which is what they usually mitigate the technical debt with refactoring. So that's that term there. And a lot of people who come into new jobs, especially like junior engineers, or even just regular engineers, right? Like a lot of times you kind of don't come into like a brand new system. Like it's very rare to be like brought into like a company and do something completely brand new. Most of the time you're going to be working with legacy websites, legacy applications. And even though these things are unfun, right? Like in some ways, you have to kind of learn that first, learn the ropes in order to figure out how you're going to design much better in the future, So there's a few terms here: operability, make things for the operations team to keep the system running smoothly; simplicity, make it easy for engineers to understand the system; and evolvability, make sure that, like as you, build, you're also able to evolve, right? So that, your old legacy system can become part of the future. So these are all, key terms to think about. Again, part of this last part of the section kind of makes a lot of sense intuitively, because we all kind of sort of know about maintainability. But yeah, like the big point here is just, being able to do some of the things we've been talking about so far. Keep the system running smoothly, monitor the health of your system, look at how the system restores itself if it goes into a bad state. And this is kind of like on the point of like what we were looking at earlier. being able to track down your problems, such as system failures. And we may do these as exercises too, like kind of talking about the Disney Plus example later on. Keeping stuff up to date, security patches. That's something I think we all have to do. And then keeping tabs on how different systems affect each other. How do the systems actually talk to each other? There are a lot more highlights in here that I have. But yeah, just kind of like, again, summarizing a lot of this together. You just want to look ahead and solve problems as they come. You want to provide also documentation's like really, really important whenever you're working with, systems, and you want to make your system more maintainable. You want to also write good documentation so people can understand at a glance, okay, here's what, this thing does, or this piece of code does. Here's how I should use it. Here's how I shouldn't use it. That sort of stuff. One thing, I'm just going to like divert here, but I really like, people who write code with stuff like this. I'm going to just put here JS doc. Or if you use TypeScript, then, you kind of get that with JavaScript. But basically the idea is that you put comments that kind of like are brief, that kind of give the idea of what the function or the class or something is going to do. What kind of parameters can it take, like a title and an author, and then does it return, any kind of, output? If there is, then usually that gets defined here. So at a glance, you can say, oh yeah, this is what this, function does, rather than having to read the code. So that's really helpful, and that
Isn't
helps.
there an IDE that does this for you? I mean, I thought IntelliJ does that for you.
It
Like
depends.
it inserts those comments. I mean, you still have to fill in the business logic information, all that, but the input output, looking at the signature, it kind of generates.
It depends. I think there are some IDs that do it. I think like if you use,
Specific to JavaScript?
well, in JavaScript, JS doc, yeah, is specific. I think for PHP, there's PHP doc, and then TypeScript has one as well. But these are all just plugins that you can install on your Visual Studio Code editor, or your editor that you use. I think maybe IntelliJ might have it by default. I'm not sure.
Yeah,
We even have to install it. But for me or for Joey, I know like we use JavaScript a lot. So I think we use JS doc, or we're supposed to use JS doc. Again, like you can see here, right? Like this is kind of like the syntax. Here's a sum function. You can see it returns a type number, but it takes two numbers, A and B. So this is like really, really helpful, in terms of, I think, let's see here, PHP doc has it too. There might be one for each language. So you just have to kind of like, look for documentation, editors or plugins or some kind of like documenter, like plugin service, and that'll help. And you can find it for probably the language you're using. So,
so how do you, just wanted to ask, so how do you, I know that, I don't know how it's exactly done, but there are ways to fail the build if you don't follow certain coding best practices, like including the documentation that if you added a method and you didn't include the documentation, the build, basically the what's that called? We have I forgot the name, but there is a rule that you write in your forgot the name, but anyway, so basically you can define a set of rules that enforce the coding standard to meet, right? The spacing,
linting, is that what you're talking about? Like lint rules, or
yeah, lint is
like
lint. Yeah, for JavaScript it's lint, I guess, right? For
build rules?
Java there is something else, I forgot the name.
Yeah. Okay. Yeah. Like, yeah, you can have like specific rules so that, if your build fails beforehand, before you compile it, right? Or before you, send it to production code, right? To be merged.
Right.
There are ways you can, and actually that's a great thing. Like, I think they talk about that here too as well. If you like, I think for me, right, like I've had some experience using this tool. I use it on the GitHub. So let's see here. I'll just quickly bring that up. I think we even have it like in our group's open source repository. I just want to kind of go through here. So like if you look at this one, React components, I think, let's see here, if you look at pull requests, if you make a pull request, I believe, let's see here, there is a script that kicks in, maybe need some time to be fixed or something like that. But I think we had a script in here that basically was, you know, checking before you push something, it would check your code and lint it. It would, and if it failed, then essentially you couldn't merge it with the code. I'm trying to find an example of that. Maybe this project had it or it didn't. But I know you can set it up here with things like GitHub Actions, and it'll test your code, right?
Yeah.
And then you can see the logs of where it failed or where it did well.
Okay. So you are essentially a JavaScript developer, Vijay. Is that your main
That's correct.
Okay.
I'm a JavaScript developer. I've been doing that for a long time. JavaScript and React and Angular and all these different things. So
Nice. Yeah, JavaScript. I mean, I did, like I have some experience, but coming from Java, I had quite a steep learning curve trying to get something working in React. But yeah,
I think it's, you know, like I think it's a little harder because it doesn't have the type system that Java has. But you know, if you can get past that and you can kind of just play around with more of the DOM, that becomes kind of fun, especially if you see like the stuff you're making, you can see like it kind of like come alive in the DOM with tools like React, and you can play around with it. So I've always liked the interactivity component of JavaScript, you know, whereas Java, it's more you have to compile things first, and then, you know,
Yeah.
you can see your output. So you
Okay.
get your output on the fly.
Yeah.
Okay, so I'm gonna kind of go through and finish this out because I know that we want to get through this and finish.
Yeah.
So the last part here is just, I think I mentioned this earlier, is, and we were just talking about it actually. So so you want to like refactor, you want to like pay attention to tech debt. And then, you know, like you want to abstract as you go, right? Like I think that's how you evolve your code. If you can make your code, you know, more of an abstraction and hide, you know, complexity, then that makes it easier for other people to, you know, work with your code. And I had a boss that, you know, used to practice this with me, and he would say like, essentially your code should be like a black box. You know, we just give it an input and then we get an output, and we don't need to care internally about what that code does. You know, other than like if that code is like a choke point for us, then we want to like evaluate. But if it does its the job correctly, you know, like if you use Hazelcast, this is a black box. You just expect that you're going to get an output. And so that's the expectation that all programmers are trying to build up to, that they're providing some kind of program or service that, you know, we can use, and we don't have to care about the internals, but we just know they're getting managed directly. So that's what a high level programming language like Python is. You can use Python instead of Java and write simpler syntax and basically expect that a lot of the lower level stuff gets done. Whereas in Java, you have to kind of think about lower level programming details. And then we talked about test-driven development, and those are tools that you can use to basically like integrate some of that. So like as you're writing like components for JavaScript, you can write test components, and then you can create like actions that look at, you know, those test components. And so the idea is that like, you know, your code is working, your code is broken until it's working, right? So That's the red.
Do you
green.
guys actually do this?
Yeah, we actually do this.
Oh, interesting.
I actually do the TDD. So when I develop, I write
Just write
out
a test.
mhm, mhm, what I'm looking to do, and then it's broken by default. But then like I make it work, right? And then when it's green, then I know that that checkbox is finished, or that particular feature is finished, right? And I do it unit test, then integration test, and then like the whole thing we test, right? Like end to end.
So ideally, they want everything abstracted, huh? Like almost like a minification, so it's more optimized.
Exactly, because if everything is abstracted, then it's easier to, just kind of operate and evolve, which is kind of like the theme of this last part right here. And
It's
so,
like less operations that the compiler has to read, huh?
mhm. Or the team has to work with. They
Got
can
it.
kind of, use the thing and be like, oh yeah, cool. Like none of us have to worry about how React works, right? We just use it.
Right.
That's a good thing. If we had
Create
to worry
React
about
app.
how React
Go.
works, yeah, we're in trouble. Yeah. So yeah, we did it. We got through.
Good job. I don't know if you still have the energy to speak through the second chapter next class. I can
Oh
I
yeah.
can do the talking if you want to take rest.
I could too.
Yeah, it's up to you. If you want to go keep talking, that's fine. But
I don't mind.
I would yeah, Joey said he would want to talk.
Yeah, I don't mind.
I think
I'm pretty
both
good at
of you-
reading.
so like I'm not gonna say one person or
Yeah.
everybody should do it. We all
That
should
sounds
do it.
good.
Yeah.
Right. Yeah. Okay. So good job, Vijay, on the first chapter. So yeah, I had but yeah, you should still bring up your Kindle version so we can share, right? Like, yeah, I have a hard copy.
Okay,
Yeah.
when's the next meetup?
So it'll be Friday, and then
Friday. Okay, so Mondays and Fridays.
yeah, but I'm gonna probably change the schedule a little bit because I think I won't do anything this week, but maybe next week I may start these on Wednesdays instead because I have been getting some requests for that. So
Okay,
do you
I'm
mean-
open to it. That's fine with me.
Yep.
And
And
then-
they works better actually.
So it'll be Wednesday morning and then Friday morning. And then what I might do is like, I might create like a small forum or something so people can also post. Because I know I have said Discord a couple times, but it would be nice to be able to just have like a forum where you can search and ask questions. So I think I might just throw one up and then we'll go with that instead. So details
I
on
think
that.
the reason for using Slack is that I don't know if I can install Discord on my office laptop. Slack would have been it's installed in all machines, right? So
You can use Slack. I have a Slack channel too. Like I just don't advertise it as much because like I don't know. I don't know why. I just went
no,
with-
like you should not migrate if you're already a power user of this thing. But I was just saying that like people might have objections to installing another tool and at least not on the
Okay.
laptops. But anyway, I think I have no issues, but I think that's kind of blocking people from adopting Discord.
Okay. So we'll get that unblocked. I think like if there's a big issue with using Discord, I think we can move to Slack or we can look at a forum.
It's the least resistance path. They just have to sign into a workspace, they'll do that.
Right. This is our choke point, right? This is our
Yeah.
is like our issue, right? Our outliers are having trouble with Discord, so we'll have to like figure out a game plan.
Yeah. I'm amazed at your energy. Like you do open source work full time, read books.
Oh yeah. Well, I mean, like I'm just like really like passionate about the whole thing. I know honestly like I've been self-taught for a long time, and I don't know, it's fun to me, and like if I do this properly, like I actually like get recognized more at work. So it's like it's kind of a win-win.
Hey, this book's a pretty fun read though. Like I don't find this boring. Like you know what I mean? Like reading about this. Like some books I read, And it's like, okay, you know, you're just kind of going through the data, you're just kind of going through the motions, you know. But like for this one, like I felt like it's actually a pretty good read. Like I feel like I've been like pretty sucked in by it, you know what I mean? Like it's
Yeah.
pretty cool stuff to think about and to know about, you know. I
Yeah.
mean, I don't
Yeah.
know. That's
And
just my take, you know. Someone else might find it boring, but I like this stuff.
yeah, and actually on like just to kind of give you like one more reason why I have the energy for it. It's just that like I feel like when I read or watch like videos or like understand more about like programming and software
Yeah.
engineering in general, like it makes my life better too, because like, you know, I can come back and be like, when I'm looking at like things I have to do around my house, you know, like the old days, I'd be like, man, I got to do laundry, I got to do the dishwashing, I got to do all this different stuff. And it would just be like so boring and annoying to me. But now like with system design, you know, it sounds so dumb, right? But like I feel like I'm able to engineer like better solutions for myself so that I'm not like doing as many boring tasks at home. And I can have more time to study. You know?
I'm gonna
So-
apply this logic to everything I do. I'll be a robot.
Yeah. Okay. See you Friday. Okay.
Okay, guys. You guys have a great day today, huh? See you Friday.
All right. Yeah. See you all Friday.
Have a good day. Bye-bye.
Bye.